तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last two lectures, we have discussed concepts of illumination and shading. First, we understood the concept of the process of illumination by light sources and understood why it is a very hard problem to solve. Then we of course, went through a few concepts based on the ambient illumination model and diffuse reflection models, where we simplify and make certain assumptions to solve the or counter the hardness of the problem. And we have also seen that the illumination consists of three parts: the diffused, the specular and the ambient term. And of course, we have studied at length the ambient reflection component of the illumination and also the diffused. Okay. And we just introduced at the end of the last class the specular component of reflection, which we are going to study in details in this class today. So, if you look into the slide now, the specular reflection is observed on a shiny surface, unlike in the case of ambient or the diffuse term, which reflects light equally in all directions. Ambient component is responsible due to interreflected rays, many of them which combine together and fall on a particular surface. And of course, we have also seen the effect of distance or atmospheric attenuation, specifically in the case of diffuse reflection. And the case of diffuse reflection are the wall, the case of movie screens, projected screens are examples of the diffused patterns. Of course, dull matte surfaces also are the case, and in the case of specular component, shiny surfaces, mirrored of course is the perfect shiny surface, and of course, there are other non-mirrored type specular surfaces. Examples are being an apple surface, shiny plastics, gold and silver coated metal surfaces, etc. So, what is the equation which governs the specularity? This is one of the models suggested by Phong. The Fong's illumination model, which we consider here, is that we have an ambient term here, where I A lambda is the ambient color, K is the ambient's reflection coefficient, O D lambda is represents the object's diffuse color, of course, which goes into the ambient term as well. Then we have seen the F attenuation term based on distance and depth. I P lambda is the point's light source intensity, I P or I P lambda is the point's light source intensity, and within that there are two terms, K D O D cosine of theta, which we have seen earlier is the diffuse component of illumination. K D is the reflection coefficient of the diffuse term, O D lambda is the object's diffuse color, cosine of theta is the angle between the surface normal n and the source, light source direction vector S. This is the new term which comes here, Ks, Os lambda and cosine to the power m, where Ks is the specular reflection coefficient varying from 0 to 1, as like Ka and Kd, we also have the specular reflection coefficient of the object surface. We also have Os lambda, which is the represents the object's specular color. Like we have the object diffuse color here, O D lambda, we have the object specular color, which could be different from object diffuse color. Okay. And cosine alpha to the power m, this is the important part. So, this is the exponent alpha, we will see is the angle between the vectors r and v. We will see, come back to that figure once again and see that this is the angle alpha between the vector r. What was that vector r? That was the direction through which the majority of the rays will be reflected, the entire intensity almost. In the case of a mirror, of course, the entire intensity goes along R, the light intensity. But in the case of non-mirror type specular, which is shiny but not mirror, majority of these rays will go along R, but a certain section will go along a direction which is close towards the vector R, and that will be dictated by the angle alpha. So, if you are close to the R, if alpha is equal to 0, the V and R are exactly same. Okay. So, that is what will happen if alpha is equal to 0, that means you are looking along R. Okay. But you could be looking around close to R, and that is the angle alpha, which will dictate how much of the intensity you are seeing, which is not along the reflected direction, all right, but close to that. Okay. So, we look back into the figure and study what is the effect of alpha, and then what is the effect of this integer value m, okay, on the specularity of the surface. So, if you look into this set of equations and the figure, let us understand the figure again. Object point O, surface normal n, source direction S. Okay, these are the two vectors, the surface normal n vector and the vector pointing to the source direction, the angle theta in between them, and the vector r pointing to the direction of in such a manner that the angle between n and r is also theta. And again I repeat, like I mentioned this in the last class, that the vectors r, n and s all lie in the same plane. Okay. So, assume a 2-dimensional scenario of r, n and s vectors, and this is the angle alpha which I am introducing now. This is the angle alpha between the vectors v, v is the viewer direction vector, and the angle alpha is the vector between the vectors r and v. Okay. Now, v could be anywhere in 3D. So, the angle alpha which is shown may not be in the same plane as r, n and s. So, you know that there is no way we can talk about saying that alpha plus theta is your angle phi, which we talked about earlier. So, you can't say that right now, because this is, as I said before, r, n and s are lying in a plane, but v may not lie in that plane. So, you have an angle alpha. So, that is the significance of the angle alpha, which we had seen in the previous slide. This is the angle alpha which I talked about. Okay. So, that is the specular component. This is the specular component. We have this specular reflection coefficient here, and the specular object specular color OS lambda, and we had introduced what is alpha. We will look at m later on, cosine of angle alpha, where the alpha is given by this particular angle here. Now, how do you compute this cosine of alpha given a vector v, n and r, s? The first question comes is how we compute r. This is given on the top, the method of obtaining alpha, and I leave it as an exercise. The first home exercise in this topic of illumination shading is to try if vectors n and s are unit vectors of the surface normal and the source direction, then you should be able to obtain that the r plus s, the vector sum of r and s, can be written as 2n multiplied by a dot product n dot s. Remember, this n dot s is a scalar quantity. So, it is a 2 multiplied by this scalar quantity n dot s, which is, you know, it is cosine of theta, because if n and s are nothing but your normal vectors, unit vectors, then this is 2. So, this value become 2. So, twice of the normal vector along and twice cos theta, I am sorry, twice of cosine of theta along the vector n will be the sum of the products, sum of the vectors r plus s. So, I leave that as an exercise for you to find out that first part. If you can derive that, the rest part of the derivation is going to be very easy, where we had seen that the sum product of r and s will be twice of that vector n and multiplied by the cosine of theta. So, repeat that, this is the cosine of theta term here, which is n dot s, we had seen that earlier, and you can rewrite this equation in this following form, where r, take this on the right hand side. So, that is what comes out from here to here, that is what you have as your r, and the cosine of alpha is the dot product we have seen between. We can see easily from the figure that cosine of alpha is the dot product between the vector v and the vector r. Okay. So, that is given by cosine of alpha, which is the dot product of r dot v, and you substitute the expression from r which you have here onto this. So, it is v dot product of v with r, where r is obtained in the previous expression. So, substitute it here, that is how you obtain your cosine of alpha. Okay. cosine of theta, you know that it can be easily obtained by a dot product of n dot s, which you substitute. So, this is a cosine of theta here, and since v, n and s are known to you, that is the wavelet direction is known, surface normal is known, source direction is known. If these three are known, you do not have to worry separately calculate r, that is inherently present in this expression which I have given in this current slide, the last one. Using v, n and s, you can obtain the cosine of alpha term. Okay, so, I look back into the figure here, cosine of alpha is necessary for you to compute, because you will need that in this expression here to compute the overall intensity of the Fong's illumination model. So, you calculate cosine of alpha using an expression given here based on v, n and s. So, if v, n and s are known, you can compute cosine of alpha. And what are v, n and s? You know that viewer direction, surface normal and source direction. If you know that, you can use this expression to compute your cosine of alpha term, use that cosine of alpha to substitute back in the overall Fong's illumination model, to which is the sum of all the three components. If you look back, the Fong's illumination model is the sum of the ambient term, of course, the attenuation factor here, but then you have the diffuse and the specular component. So, sum of basically three components: specular, diffuse and an ambient term. Of course, the effect of distance does affect the specular and the diffuse term, it does not affect the ambient term for that matter, and that is what the Fong's illumination model tries to capture. Okay. And you know how to, you set the ambient term, you calculate the diffuse component beside a cosine of theta based on the angle between the normal and the source direction, and then of course, you have the specular component contributed to by the cosine of alpha term, which is computed by this particular expression as given here. Okay. So, this is how the three components of the Fong's illumination model are considered. So, I repeat again, there you have the ambient term, the diffuse term and the specular term. All the three terms we have studied, and of course, also the attenuation term based on distance. The only factor which is left to understand in the Fong's illumination model is cosine alpha to the power m, cosine to the power m. How does that factor affect the specular component? If you look back into this expression here, this is the term which is only unknown, otherwise you can set all these terms, compute the cosine of theta, you know how to compute cosine of alpha now, we have seen all these expressions, but what is this m doing here and what is its role to play? Can we put m equal to 1, or what should be this value of m depending upon the specular nature of the object surface? So, let us try to understand the effect of m. This is a cosine curve for m is equal to 1. So, that is a cosine of alpha, the x axis is alpha and the y axis is cosine of alpha. Okay. You can visualize, you can draw, you know the sine and the cosine curve. So, this is the cosine curve, the x axis is in radians running from minus pi by 2 to about plus pi by 2, that is the range of m in radians, range of alpha in radians, or range of theta, or you can take in this case alpha running from minus pi by 2 to plus pi by 2, and you know it varies from 0 to 1 and falls back. So, this is the cosine of alpha for m is equal to 1. You know the cosine of theta function, cosine of x function or cosine of alpha function. Now, if I raise cosine square, cosine cube, what do you think the function will change? Okay. What will the function look like? Okay. Try to visualize and draw it yourself. Take a cos x versus x curve from 0 to pi by 2 or even minus pi by 2 to plus pi by 2. You can try that with sine also, but take the cosine in this case, because that is where what is going to dictate my specular component of the illumination, minus pi by 2 to plus pi by 2. It varies. That is the cosine of x. Cos square x, cos cube x, what will, remember it is a fractional number between 0 to 1. So, fractional values, when you take square, it will start going down, and so let us look at a value when m is equal to 3. This is how it will look like. Square, it will look in between. So, if this is cosine of x or cosine of alpha versus alpha, this is cosine alpha cube or cosine cube alpha, okay, and versus alpha, and again ranging from 0 to pi. If I raise the m further, you increase the value to a very larger value, say m equal to 11, this is what you have. Okay. So, as you can see, the curve is getting narrower and narrower. Cosine of alpha was a broader curve between minus pi by 2 to plus pi by 2. Cos cube, it became narrower. Cosine of to the alpha to the power 11, or even higher if you take larger and larger values of m, you can superimpose these 3 curves yourself in mind or on the paper and draw it yourself and see that the curve is getting narrower and narrower. Let us repeat this. This is the cosine of alpha itself when m is equal to 1, m equal to 3 means cosine cube, this curve will look like this, and this is cosine to the power 11. So, as you can see, the curve is getting narrower and narrower. Now, cast your mind to what was this alpha. This alpha was the angle between r and v, and we were saying that majority of these rays which are reflected by a specular object surface travels along the direction of r, a small fraction of that gets distributed around that vector r in 3D. So, you can visualize as if you have a cone, you visualize a cone in 3D at the vertex at that object O, and that axis of that cone is along the vector r. Okay. If you go back to this figure and visualize yourself that you have a cone with the apex or vertex of that cone at object O, and the axis of that cone is travelling along r, and so the cone is here somewhere with the axis along the direction r and the vertex at O, and the v is on the surface of that cone. So, you can visualize as if you have a cone going along r, and the angle alpha is the angle of that width or view of that cone subtended at that vertex. Angle subjected at the vertex of that cone is the angle alpha. So, if you reduce alpha to almost 0, of course, the majority of the rays are going along that direction, which is r. Okay. As you keep increasing alpha, you are talking about a larger and larger cone, okay. And there are certain rays which are not going along, travelling along or reflected along that direction r, but also travelling around in that semi infinite volume given by that cone at that subject O. And what percentage of rays will be travelling along that r, and what are the remaining percentage of that will be spread around in that cone or conical volume will be dictated by that factor m. Alpha will dictate the angle between r and v, basically that how much is that cone width is, but in that conical volume how much will be reflected along r and the surrounding will be reflected, but that m will try to capture the fraction of that light energy or light rays which predominantly go along r, and rest of it, the remaining percentage travel along or around side in that conical semi infinite volume. I hope I am able to give that figure, because if now asymptotically start thinking, you have seen the nature of that cosine to the power m, okay, cosine curve, cosine cube and cosine to the power 11. So, it is getting narrower and narrower, as you can see here. This was the cosine curve, cosine to the power 3, cosine to the power 11, and assume that the tip of that cone is at this point where the value of alpha is equal to 0. It is always equal to 1. You know, when alpha is equal to 0, the cosine raised to the power any quantity will be always equal to 1. It is here also 1 and it is also here 1. So, that value is alpha is equal to 0. So, when the v and r coincide, but as you start moving outside, how much of percentage will go will depend upon this nature of the value of m, in fact, is going to dictate. So, can you tell me now, for a perfect shiny surface which is a perfect specular like a mirror, the mirror is a example of a perfect specular mirror type or mirror surface itself, what should be the value of m? Because all the rays will go only along r, nothing will be going outside in that conical volume. So, for any alpha which is non-zero, the amount of light which you get is 0. When can you achieve that? With this cosine to the power m function, when m reaches a very large value, as large as you can imagine, infinity virtually. Okay, asymptotically you have to visualize the cosine to the power m function when m reaches a very large value, as large as you can imagine, infinity. In fact, that is the case when you reach the mirror, case of the mirror reflecting all of the light only towards the r direction, that is the case when alpha is equal to 0. So, when v and r coincide, in the case of a mirror you are seeing the all amount of light. The moment the v comes out of r, that means you have a non-zero value of alpha. If this is say the r and the v does not coincide and is just coming out of the value r, there is a difference between the v and r, they are not same, then you have a non-zero value of alpha, and when cosine is raised to the power of very large value, virtually infinity, then for any other non-zero value of alpha, the value shoots down, like an impulse function is what you will have, where the value is very large or 1 in fact at a value when alpha is equal to 0. For any other non-zero value, it is 0. So, that is the case for an, so you the case of a mirror where you model that with a large value of m. Now, what does that mean? That also gives us a tool to vary or tune your m depending upon the type of the specular surface which you have, which is of non-mirrored type, but specular, you tune your value m. You do not have a control of the alpha. Why? Because the alpha is the angle actually present between the v and the r. V word will be at a certain direction. So, based on that you will have a vector v, and the angle between v and r is your alpha, which you know how to compute based on the equations which you have seen. But how will you set the angle alpha? Alpha is what you compute, m is what you set based on the object's specular reflection property. Of course, the Ks term is also there in terms of about how much of light it will reflect. It might absorb a few, okay, that will be. So, Ks is considered to be 1 if all of the light is reflected like in the case of a mirror, but non-mirrored type specular surfaces might absorb a few percentage of the light. So, the Ks may drop just below 1, maybe 0.9, 0.99, 0.95, depending upon whether you are talking of a very shiny surface, apple type, gold or silver coated surface, those values of the Ks will be close to 1, but less than 1. But more than that, since it is non-mirror type, the value of m will not be infinity, it will be a finite large value, more than 1 of course. So, you set that value to 1, 2, 5, 10, 20 or even 100 will depend upon the surface property, because that will dictate how much percentage is going along R and how much you are able to see around that R in a conical semi-infinite volume. Based upon the V, assume that V to be moving around that R. If it is too far away, it sees very less. The more it gets closer to R, that means the value of alpha getting close to 0. When V asymptotically starts reaching or getting close to the value of R vector, V and R getting close together, the alpha gets smaller and smaller. When R and V are same, alpha is 0. That much you know. But if it is non-zero, in the case of a mirror, you do not say anything. There is no doubt about it, because you just put the value m to be infinity and you can visualize an impulse function, value of alpha non-zero, you do not say anything. But non-mirror type, please understand this, non-mirror type specular reflection, when you have, then you see majority of that when alpha is equal to 0, but when alpha is non-zero, you also see some percentage. What degree it tapers off, how much percentage of the light falls over, in what nature it tapers off will depend on the value of m you select. So, more closer to a mirror type, you choose a large value of m, more closer to a dull type specular reflection, you choose a lower value of m, around 1 or 2. Okay, this is how you change the value of m, and that is how you control the degree of specular reflection, not the coefficient, specular reflectivity. So, coming back here, this is how you compute alpha or the cosine alpha, and then based on the closeness of the V to R, you control the term here. The m will dictate the amount of specularity in terms of the Fong's illumination model, and we know how m varies. When you vary m, what is the degree by which the light rays or the light intensity a viewer is able to see. This is the value of the cosine alpha, cosine cube, cosine to the power 11. Okay. And as you go higher and higher, this region will start reducing with reducing values of alpha or theta, and it will start to taper to 0 much earlier, around 0. Okay. So, the last few points regarding the Fong's illumination: if the light source is at infinity, the angle between n dot s is a constant, whereas r dot v varies across a polygon. So, that we assume in a Fong's illumination case, that if the light source is a special case, when the light source is at infinity, the angle between n and s is constant. It is the angle theta which we talked about earlier in the case of diffuse reflection. This is valid the same when s is at infinity. Let us take the situation of the sun, source of the light rays from the sun. If you travel anywhere in the city at any given point of time, the light source appears in the same direction. Of course, if you travel across a country from one region to another, yes, the light source may not appear to be the same direction, all right, but typically if you move around somewhere close by, even around a building in an open space around a field, the light source, the sun, which is virtually at infinity. Even of course, if you move to say to nearby cities, very nearby, just the distance of about say a few tens of kilometers or up to 100 kilometers or even less than that, the light source direction of the sun remains the same. So, S dot n, since n is same for a particular object, S is same if this light source is at infinity, n dot S, the dot product cosine theta, is also a constant if the light source is at infinity. Okay. And whereas R dot V varies across a polygon, because the viewer direction could change. You could look at the polygon from different direction. For curve surfaces and light source at finite distance, both these factors vary across the surface. This is very interesting. When talking of a curved surface, you cannot now assume that also S could be constant, but the n could vary for a curved surface. Assume a corrugated surface, a sinusoid variation like an asbestos sheet is a very good example, or any random type of a curved surface. It could be a Gaussian, spherical type, conical type, cylindrical type, those are again circular. We can take a Gaussian type of a variation or a sinusoidal asbestos sheet. At each point, to each point, the surface normal varies, and if that varies, n dot S will also vary, that is the cosine theta term, that is number one. Cosine of alpha might also vary, because the n dot V, that phi also changes, and hence it will cause that R also to change. So, the cosine alpha will also vary, because that is the angle between V and R. R will vary because n is varying. So, for curved surfaces and light source at a finite distance, both these factors theta, phi and alpha, all of them will vary, causing the Fong's illumination to be computed at each and every point. Whereas for a planar surface, light source at infinity, if we compute at one point, all close by surface for a planar surface will have the same intensity. It will not vary much. Even for a slowly varying curved surface, it will almost be the same. You do not need to, you can actually use some incremental computation to compute that, okay, to perform the computation. Whereas for finite distance light source and for curved surfaces, you have to compute that for each and every point. So, these are the 2 points which you keep in mind. I again repeat, if the light source is at infinity, the angle between n dot S, and hence the angle given by n dot S, which is the cosine of theta, is constant, whereas the R dot V, which is the cosine of alpha, varies across a polygon. For curved surfaces and light source at finite distance, both these factors vary across a surface. There is a way called a halfway vector H, which is used to simplify the computations for the cosine of alpha. If you look at this figure, we know what is n earlier, we know what is S, we know what is R also, and we know to compute this R given n and S. The angle between n and S is cosine of theta, it is the same angle between the R and H, R and N. The angle between V and R is an alpha, so it is a 3-dimensional figure. R, N and S, again I repeat, lies in a plane, but this may not be the case when between the V and the R, okay, because that is in 3D. We introduce a halfway vector H, which is a vector between the light source and the viewing vector V. So, V, H and S now lies in one plane, R, N and S lies in another plane. It is very interesting for you to visualize. You can visualize 2 planes, N given, S given, V given. Now, N, S and V are not lying in a plane, but I can construct a vector R given N and S, N here, say S there, and your V there, the R there. I can construct this R which lies in the same place as N and V. Now, given V and S, which lies on maybe in one plane, but not in the same plane as R, N and S, I visualize a plane consisting of the vectors V and S. I construct a halfway vector H, which lies between V and S as N was lying between R and S. Okay. That halfway vector is a bisector vector between V and S and lies between the plane V and S. So, V, H and S, I repeat, V, H and S lies in one plane, R, N and S lies in some other plane. And if that is so, and then we can compute this vector H given this particular equation S and V. That is very simple to compute, given S and V. This is some vector product on the numerator, and the Euclidean norm at the denominator, S plus V vector. You take the Euclidean norm. So, just you do that to assume that H is also a unit vector. but it is in the plane between V and S, different from the plane of R n and S, and if that is so, that is a half wave vector H. If the light source and the viewer are both at infinity, you can compute this H, and the specular term now gets modified to a simpler form by trying to compute the cosine of beta to the power m. So, we assume that the beta and alpha are approximately same. Okay. That is the, remember, you have to visualize that V, H and S are in one plane, R, N and S are in some other plane, and whatever is the angle alpha between V and R, it is the same as the angle beta which is between H and N. H and N are not in the, you can of course visualize it is a plane, but remember you have to visualize this figure in 3D. I again repeat, R, N and S are in one plane, V, H and S is in some other plane, and the angle alpha between V and R is the same as the angle beta between N and H. Okay. So, cosine is of beta is nothing but the dot product between N and H. Take the dot product between the vectors N and H, that is your cosine of beta, raise it to the power n, and since N is known, H can be simply computed as given in the figure equation here. You can compute the cosine of alpha as equivalent to cosine of beta and raise it to the power m easily. So, this is another method by which you can simplify the computation of your specular term in the Fong's illumination model. I repeat, just this, look at this equation once again, you just replace the all those previous equations by the n dot h and raise it to the power m. So, that is what you have for, if there are L light sources, then the formula is given as this, that you have to sum it for all the different light sources, because I p lambda will now vary. In fact, the I will probably vary here. You can visualize this p as the equivalent to the index I, which varies for L different light sources, because the expression was given earlier without for a single light source. So, if you have L light sources, you have to sum these different terms. Ambient typically does not change, but the diffused nature of the surface and the specularity terms will change for L different light sources. Okay. But here there is a danger with, if you use this equation, you may need to normalize the color intensity value or clamp it or choose coefficients appropriately or displace in the log scale to ensure that the I lambda term does not cross 1. Typically, you always normalize intensity values between 0 and 1. So, you must choose these coefficients. What are the coefficients? K, Ks, Kd, which also could lie between 0 to 1. Remember, and then the intensity values also lie between 0 to 1. The cosine of theta, which is the dot product between these two vectors, n dot h or n dot s, also will lie between 0 to 1. So, these are all fractional numbers, but sum of all these fractional numbers, if there are L light sources plus the ambient term, may actually give you a value which is more than 1. Okay. So, you should be careful that when you are choosing these terms, you always have a resultant light intensity normalized range between 0 to 1, and there are many ways to do this. The typical ways, if you look back to these steps, are you actually calculate whatever you get, even if it is more than 1, you at the end normalize the color intensity value between 0 to 1, or clamp it. Clamp it means if you have a value of I lambda crossing 1, do not consider any values more than 1. If you have 1.5, clamp it to 1, clamping of signals, okay, in electronic circuits. So, if you have 1.1, always clamp it, just throw out the value which is more than 1, and I mean not totally, just clamp it at the value 1. Any value which you get more than 1, clamp it to a value 1, or choose the coefficients appropriately. That means you have to choose all these I a lambda, K a, O d lambda, I p lambda, K d, K s, and all these objects of phase, color and reflection coefficient in such a manner that with L light sources, L being a number which is more than 1, 2, 3, 4 or 5. As I said before, up beyond a certain point, the light sources, if you increase, of course, the brightness will become very bright, but it will not cross a certain value. You have to choose those terms carefully such that even with larger number of light sources, the resultant time I lambda term which you get as a resultant sum should not cross lambda. So, that is one way. So, three methods are: normalize the color intensity after addition of all of these terms, clamp it, that means restrict to the value 1, or choose coefficients appropriately, so that you never have a value close than 1. But it is difficult to choose coefficients appropriately, means you have to choose the values very less. That is not a very good idea. You have to choose it appropriately, all right, but as you keep on increasing the value of all, there is always a scope mathematically, hypothetically or theoretically, but the value shoots up beyond 1. So, in that case you have to normalize it or clamp it. There is another method talked about at the end, where you display in log scale. And when does it happen? When do you actually display a signal in log scale? Light intensity also can be visualized as a signal. When do you display in log scale? You display that in log scale when you have a dynamic range of signals or gray level values of a pixel very large. because what will happen is most of the values are very bright. The surfaces which are only receiving ambient light will have a small value of intensity, say 0.1 or even less than that, say 0.01, 0.05, 0.02 in that range. And if you have many bright parts of the scene with values around 0.7, 0.8, 0.9 or more close to 1, then what will happen is those will become so bright and dominate the scene that the ambient term will not be visible. So, in order to do that, what is typically done is you display in log scale, because the dynamic range in the log scale will be reduced, okay, and that is what you use often for most signal processing amplifiers. Also use logarithm scale for displaying. For dynamic range of scales of signals are very large, you use that in the case of displaying illumination effects when the ranges are very large. From a very small range, fractional number 0.001, say you have values around up to 0.99. When you have values around 0.9 or more, values around 0.1, why? Even 2 or less will not be visible to the naked eye when you display them on the screen. So, display that in log scale. That is also another method by which this illumination dynamic range of pixel values are handled. Reflectance properties are a very important one. You have the Lambertian model, which we talked about for diffuse reflection. This is an example of a Lambertian surface. We will go through lots of examples now in the remaining time which we have. This is independent of the viewer. As you can see here, Kd cos theta, theta is the angle between n and s. So, whatever v you put, you can change your viewer direction here and keep rotating the object surface, you will get the same illumination. This is the example of a Lambertian or diffuse surface of the ball with red color. Okay. Let us look at the Phong model, which has two terms, which has the diffuse reflection and also the specular reflection part here. So, I will show you two examples. And I hope sincerely that the picture is very clear. The left hand side picture has a diffuse reflection coefficient of 0.3 and specular component of 0.7, the m is 2. So, that means this surface has a large value, because remember Kd and Ks are ranging from 0 to 1 and the value m is an integer value typically taken, or it could be a fractional value also. Larger value of m, larger value of Ks indicates it is this term is dominating. That is, the specular component is dominating. It is a very shiny surface, the light surface is reflected here. The same case is not here, there is no specularity here. Mirror type reflection is not happening in the Lambertian diffuse surface, but it is happening here where the surface is more shiny here, less shiny here. Okay. So, because the diffuse component is less, that is what you have. Now, if I change Kd to 0.7 as given in this figure, that means increase the diffusion component and reduce the specular component from 0.7 to 0.3, the exponent is also reduced from 2 to 0.5, you see the resultant effect. That means it has a small effect or an insignificant effect of specularity or mirror type, more of diffuse. This result is more closer to the absolute Lambertian surface. Most of it is Lambertian, a small amount of specularity exists, whereas in this case the Lambertian effect is very small or diffuse effect is very small, most predominant effect of mirror type specular reflection more at the center, as I was talking about. When alpha is increasing and you are looking to the outside surface like a cone, the effect of specularity or the light reflected due to specular reflection, it will be less as you keep changing your alpha. So, I hope these three figures tell you the difference between pure Lambertian surface. Of course, pure specular surface is a mirror, which I do not have to demonstrate. You can see yourself in front of a mirror and or put a torchlight source and see what happens. But other than that, pure diffuse surface, more specularity, and a combination of a specularity and diffuse, where we have seen two cases where the specularity dominates in one case and the diffusion one dominates in the other one. I ask you to look back into the figure. This is pure diffusion. These two figures is a Phong model where the specularity dominates here and the diffuse part dominates here. So, this is the Phong's model, and it is a very nice example to show how when you vary the diffuse reflection coefficient and the specular reflection coefficient, higher Ks here, higher Kd here, and the m also you vary, what are the different factors here. You can visualize in the Lambertian surface that there is no Ks is equal to, can be visualized to be 0, okay, and m also can be visualized to be a very small quantity, close to 0. Okay. Now, let us look at shading models for polygon. Now, there are various ways by shading models are done. This is a constant or faceted shading or flat shading. As you can see, this is a wireframe diagram of a sphere where all internal parts of a polygon, in this case quadrilateral triangle, whatever you get has uniform illumination all throughout. Okay. As you move from left to right, of course, there will be could be variations or bottom to top. You assume here that the light source is in the top, so the top has more, but each particular polygon has the same intensity. So, you compute the surface normal and the same intensity you give for the entire polygon, a quadrilateral or triangle. So, that is why it is called a constant shading, or also called faceted or flat shading. So, this is an example of a flat shading. Yeah, we continue with flat shading. If I remove the wireframe diagram, this is the illumination which you get. The illumination surface is illuminated from the top. So, you have absolute white brightness, and as you go going down, you have very less illumination, because it could be only due to the ambient term at the bottom. We will see more results. So, faceted shading is determine a single intensity value and use it to shade an entire polygon. That is what you do for a faceted shading. And the approach is valid provided that the light source is at infinity. That means the dot product of n dot s, which is cosine of theta, is constant over the entire face. That is what you do for faceted shading. The viewer is also at infinity. So, the n dot v is a constant over the entire face. It may vary in some cases, but typically it is assumed constant, and the polygon is not approximating a curved surface. If it is very curved, polygon is a very bad approximation. Okay. So, curved surfaces, we better use the curved surface representation. A polygonal piecewise approximation is not a good one, and then in that case, of course, if the entire surface is a planar one, like a cubical surface or a large sphere with slowly varying radius of curvature, then of course, polygon approximation is a good modeling and can use fast shading. But if this is sharp bend polygonal approximation, we have seen that in CSG is not a good approximation. So, faceted shading is not good. We have to go to a new model of shading called the Gouraud or smooth or interpolated shading. But going through these terms, these points once again, we assume that the light source is at infinity, viewer is at infinity, and the polygon is not approximating a curved surface. Coming out of faceted shading, which is a very coarse approximation, we look at Gouraud shading or colored intensity interpolation shading, where you see suddenly now that the interpolation is very smooth. It gives a very nice visualization of a very smooth surface. Okay. How do you get this? You look at the difference between faceted shading and Gouraud shading for the same. This is what we got earlier by this what we call as this wireframe diagram, where each polygon or triangle is having the same shade piecewise. When you go from one polygon to another, move closer towards the light source, you have different levels. So, you have this effect of aliasing in shading. You can talk about discontinuities, but it is very smooth. How to interpret this Gouraud or smooth, or what is called the interpolated shading? Okay. This is another example, okay, of the same sphere, highly coarse sphere approximation, and the light source is coming towards the frontal lighter part. As you can see, there are some back or hidden faces which does not receive any illumination, top surface is illuminated less. This is having the maximum illumination, but it is faceted or flat. This is the case. The same coarse wireframe approximation of the sphere is taken, but when you put Gouraud or smooth or interpolated shading, you see the smoothness of the intensity at least. You can see the coarseness of the representation of the sphere in terms of its structure, all right, that is due to the coarse wireframe diagram which has been taken. You can take finer structures, more less increments of this sweep representation of a sphere using a circle, but that same coarse representation when you use, you have the smooth representation of intensity using Gouraud or smooth. And you have to visualize that we have not taken a finer representation of a sweep representation of a sphere and try to and try to do shading using faceted. No, that can be done, but that is not done here. Same wireframe representation, but Gouraud or smooth interpolated shading gives such a fine picture, at least of the smoothing, if not for this surface, of the intensity variations. How do you implement the Gouraud shading? So, this is the slide which will talk about the principle of Gouraud shading or color intensity interpolation shading. Let us say if you take a triangle, and we are interested in shading this particular point, and we know that this triangle has different intensities at each point. I will not use faceted shading to shade it like the way which is illustrated in the figure. Constant gray level shading I will not do. So, what do I do to obtain this? What is known to us? We assume that the vertices of the surface at these three, the surface normal at these three vertices of the triangle are known. N1, N2, N3 are the surface normals of these three vertices 1, 2 and 3. If that is so, we can use this surface normal and then use the Fong's model to compute the intensities I1, I2 and I3 at these 3 vertices 1, 2 and 3. Okay. If that is so, that we know how to do that, because the Fong's model will tell you how the intensity I1 or I2 or I3 can be obtained from N1, N2, N3, provided the viewer direction and source direction is known. So, what is the intensity at this point? What we do is, we take a scan line, because that is what we use, scan line based filling. So, every point you will have a scan line from top to bottom or bottom to top. What do you do with this scan line? If you go back, I compute the intensity at the 2 intersection points of the scan line with the edges of the polygon. In this case, polygon is a triangle. So, I compute IA from I1 to I2 by some sort of an averaging or interpolation, and I do the same thing for IB. I use I2 and I3 intensities to compute IB. I will come to this equation soon. How to compute IA, the intersection A of this scan line with this left edge, and the IB is the intersection of this point, which is the intersection of the scan line with the right edge of the polygon. Okay. If IA and IB can be computed, IA is computed from I1 and I2 using interpolation, IB is computed from I1 and I3, then the same interpolation along x direction will give you IP, the intensity at this point. What are the equations for this? This is how you compute IA. IA is computed from I1 and I2 based on y variations. What are these yi's? Y1 is the y coordinate of point 1, which has the surface normal N1 and intensity I1. This is now you can operate this intensity part in 2D. Okay. And y2 is of course the y coordinates of this point 2, y coordinates of this point 3 is y3, and what is ys? The scan line s. Scan line for this point, the y coordinates of this scan line is given as this ys. As you can see, when ys is equal to y1, you will have the intensity IA equal to I1. This is this in linear interpolation which we have done earlier. Where have we done this linear interpolation? When we talked of atmospheric attenuation, we varied the Z from ZT to ZB in the previous lecture, and got scale ranges from SA to SB. Okay. So, you do the same thing here. As you vary Ys from Y1 to Y2, you will get IA values running from I1 to I2. Let us check this out. If Y1 is equal to Y2, okay, if Y1 is equal to Y2, you will have the negative sign here, and then I1 and I1 cancel out, IA will be equal to this I2 term. So, this IA will vary from I1 to I2 linearly using this expression. Similarly, using the second expression, IB will also vary linearly from I1 to I3. That is how this varies the IB. And if IA and IB can be calculated once the right hand terms are all known, I1, I2, I3 are computed first, and Y1, Y2 and Ys are known, then you compute IA and IB. And how do you compute IP? That is again a x interpolation along the x direction from IA to IB. As you can see here, as the XB is the x coordinate of this point B, XA is the x coordinate of this point A, and XP is the x coordinate of this point P, and that will give you the intensity IB. As you can see, if you vary XP to XA, you will get IA intensity. If you put XB equal to XB, you should be able to get IB. IP is equal to IB, and we get linear interpolation in between. That is what you have, the values ranging from IA to IB. I will roll this slide once again, which will be very interesting for you. So, what we are interested in, to given this a triangle as an example of a polygon, you are interested to get the intensity of this point. So, first thing, calculate the surface normal at these 3. If these 3 surface normals are same, we are talking of a polygon not representing a curved surface in general. In that case, flat shading can be adopted. If N1, N2, N3 are all same, you will get I1, I2, I3 also as same, and then you can uniformly fill the polygon with the same color. But that is not the case in the Gouraud shading, where we have 3 different surface normals. We will see when we get 3 different surface normals and how to calculate that surface normals, because the formula which we know is given 3 XYZ points or n different vertices, we know the surface normal of the entire polygon. How do you calculate these 3 different surface normals at 3 vertices, or n different surface normals at n different vertices of a polygon? We have to check that out. So, that we will check later on, but let us assume that with those calculations you can get N1, N2, N3, which gives you I1, I2, I3. So, use interpolation along this for this scan line. For the left intersection edge, calculate IA, by interpolating between I1 and I2, interpolate between I1 to I3 to get IB, the intersection at this point, and then linear interpolation from IA to IB to get the intersection IB, and these are the equations which you have. I hope you have copied these equations when I was discussing them. Now, coming back to N1, N2, N3, this is a very interesting principle of how do you compute the surface normal at a vertex. Let us say that this type of adjacent polygons is representing a curved surface. It is a top of a pyramid or something, or even pyramid of course could have planar surfaces, but this is a scenario where you have to visualize that you have a binding is representing a planar surface. So, the vertex is at the top and the other surface at the bottom. So, what you do is you compute using the previous formula these surface normals N1, N2, N3, N4 and N5. There are 5 different surfaces with 5 different shades. I have tried to give 5 different shades, assume some of them could be same or different, but you compute, and this we know because give them these vertex coordinates x, y, z, you know how to compute the surface normal of each of these, and then take a summation of these vectors and average to get the weaving vector surface normal of this particular NV. So, you do this for this point and you keep repeating this for all the other vertices. You take the neighboring polygons, adjacent polygons which form that vertex, okay, and calculate the surface normals of each of those polygons and get a NV. So, you get this NV, and for other vertices also do the same, and this will result in different normals at different vertices of a polygon which is representing a curved surface, because we are doing piecewise approximation. So, once you do that, what you have is basically N1, N2, N3 for a triangle, 3 different non-surface normals and 3 different intensities, okay, as given in the previous interpolated Gaussian shading example, and then you start interpolating and calculating the scan line intensities and then do an interpolation along the x-axis. If you do that, you will have this interesting smooth intensity variation as we have seen for a sphere. Let us take the example for a teapot, illustrating the difference of shading in case of a teapot, where I have used facilitated shading on the left hand side top figure, and on the right hand side it is a Gouraud or interpolated shading. So, you can see that with the same wireframe representation, you can see facilitated shading for the case of a teapot, which gives a very coarse approximation. Of course, forget the aliasing part. This aliasing is a defect which we will discuss later on, which is there with even line drawings. So, it will be there here, but you look at the Gouraud shading, the smooth, it looks like a light smooth metallic finish with a glossy part in the middle. Okay. So, you have a specularity with the Gaussian part, and so now you can see the difference between the teapot and the, and of course, you have seen that in the case of a sphere, the teapot also has a round spherical surface, and you can see that the faceted shading will have flat shading in within the quadrilaterals or within the triangles at each part, which gives this flat sort of shading over the teapot, and this you see the smoothness here. In spite of using the same wireframe structure, you can see the smoothness of the entire surface, not only here, but also on the top, on the side and the bottom and the one. So, this is a nice example for the Gouraud shading. So, we have almost come to the end of the discussion of illumination shading models. Remember, we have discussed 3 different types of shading models: ambient, diffuse and specular. We have talked about specularity, atmospheric attenuation, effect of distance. We talked about the reflectance properties, different reflection coefficients, object color, surface color being different, the Fong's model capturing all these terms, and then of course, towards the end we discussed about Gouraud shading, which gives a smoothing effect. Of course, the better wireframe, if you take a wireframe structure represents a solid or a curved object, the more finer you get, it is better, but even if you have a coarse representation of a curved object by wireframe, Gouraud shading can do a lot of intensity interpolation. That is why it is called an interpolated shading or a smooth shading or a Gouraud shading. Of course, there are effects which uses all these and concepts of reducivity to give realistic effects with the help of shadows to make a realistic scene in terms of virtual reality or visual realism. You need to combine Z buffer and ray tracing of VSD. You need to combine Fong's Gouraud shading, interpolated shading, all these terms of effect of ambient, specularity, diffuse, Gouraud shading, effect of shadows, reducivity combined together to have sophisticated shading models giving visual realism and simulate virtual reality. That is what you should try to learn yourself from advanced books and advanced papers and magazines published in good international journals, but the basic properties of illumination shading has already been covered right now. Thank you very much.